Good morning, everybody. Uh, Today our talk is by Julia Smith Wellner of the University of Houston. And as you can see, it's on ice, ocean, meltwater, and sediment at the Thwaites Glacier in Antarctica. Julia has a PhD from Bryn Mawr College, undergraduate at Bryn Mawr College, and she teaches at the University of Houston and is a sedimentologist and stratigrapher. She's worked in the Arctic and a lot in the Antarctic, and I find it quite amazing. She also takes students out to study the beach sediments in the Houston area, which I can't imagine a greater climate contrast between the Antarctic and the beach near Houston. So Julia is going to talk about the Thwaites Glacier and its implications for the future. Thank you very much, Julia. It's all yours.
Thank you very much. And thanks for this invitation to speak with you today. You're right that there is a pretty big contrast between working in Antarctica and working on the Texas coast. But I hope with this talk, you'll see that scientifically and societally, they are connected sets of questions. So I'm going to be talking to you today about Thwaites Glacier. And you heard I am a sedimentologist. There we go. There's penguins just to get it out of the way, so we don't have to worry about looking for any more biology. And what I'm going to show to you today is a little bit about why Antarctica is an important place to be working. And then I'm going to go through explaining what I and my students do, the relevance, why it matters to us, and what we have found lately. So Antarctica is the highest continent. It is about 99% covered by an ice sheet, and the average elevation is about 2,500 meters or 2.5 kilometers above sea level. Without that ice, it would be the lowest continent, but because there's so much ice everywhere across it, it's actually the highest continent. If all of that ice were to melt, global sea level would rise about 60 meters, 60. That's a huge amount of sea level rise. Most of the ice is locked over here in East Antarctica, where it remains relatively stable. We are working in West Antarctica, where the ice is more susceptible to rapid change. And we'll zoom in on that later on. Antarctica is also the driest continent. It is a polar desert. Here in Houston, we're expecting, maybe 6 inches of rain tonight and tomorrow. That's more precipitation than falls across most of Antarctica each year. And so what we see in this image is millimeters of liquid equivalent, so that's water equivalent, annual rainfall. And we see that across most of East Antarctica that we're well under 50 millimeters per year in annual snowfall. What that means is that even if the ice is melting very slowly into the ocean, there's very little precipitation falling on the continent, meaning that it's also not replenishing the snowfall very quickly. As no one's going to be surprised, Antarctica is the coldest continent. And again, we're looking at another image of the continent where we have East Antarctica is by far the coldest. That is because that is where the ice is the thickest. Remember, I said it was stable. Because it is stable, it is also very thick. And therefore, the high elevations make it quite cold. Where I work over here in West Antarctica, I work at sea level. I work in the austral summer because that's the only time you can get there. And what that means is it's not truly all that cold where I work, just below freezing, maybe -10°C. This is the last image of the Antarctic continent as a whole that I'm going to show for a while. So I just want to point out that this is the standard projection of the Antarctic continent. This is 0 degrees longitude going towards the top of the screen, the South Pole in the middle of the projection, and 180 degrees longitude towards the bottom of the screen. So you can imagine going up to Greenwich at the top. And if we go down to the bottom down here, we'd get to New Zealand. South Africa, it would be over on the right of the screen. And the Antarctic Peninsula right here sticks up almost to Chile and Argentina. That's the standard projection of how we look at the Antarctic continent with 0 degrees longitude at the top. We're going to see a few different projections as we look at more detailed images. And when I zoom in over here later on, it's going to be rotated so that north is at the top of the image and south is at the bottom of the image, just like you're used to in any other projection. But when we look at the total continent, that doesn't work. And last, I said that Antarctica is the windiest continent. That is driven by that high elevation, where air is cooled by the ice at elevation, and then due to gravity, that cold, dense air blows offshore. This becomes significant, not just because it makes it windy and difficult to work sometimes, but because that katabatic wind, the gravity-driven wind, forces the sea ice farther away from the continent, allowing upwelling of nutrients in the ice-free area, which is called a polynya. So this is a good chance here to just work on a little bit of vocabulary and define what we're going to talk about. The ice sheet is grounded ice. You can see the ice sheet is resting on the continent or on the seabed. And so that ice sheet is sitting on bedrock of some type. An ice shelf is the extension of that ice sheet, where the ice sheet is flowing out into the ocean and then goes to flotation where it's thin. There's that polynya, and then sea ice is just frozen ocean. It never was part of the ice sheet itself. Rather, it forms from the freezing of the cold water. This is a diagram that many people might know from freshman oceanography or other basic classes. It also forms the basis of a lot of general audience talk about climate change, where the thermohaline circulation, which is a density-driven global current, as water cools near Greenland, that cool water sinks, and then it flows south around the Antarctic, rises when it warms, etc. And this forms the basis for a lot of sort of general purpose climate discussions. I'm going to show you that same thermohaline circulation, but instead of just stretching Antarctica across the bottom of the image where you're kind of forgetting about it, show the same ocean current simply in a different map projection. So this is Antarctica here. So obviously that we are focused on the South Pole, but this is the lines of latitude and longitude you can see curving out. This is the type of projection where you can imagine peeling the pieces off the globe like an orange and then setting those pieces, pushing them down. And so there's no area distortion. There's obviously other types of distortion. But what you can see is that Antarctica is sitting in the middle of the world's ocean. The Arctic Ocean is a small basin at the opposite end, and Antarctica is sitting in the middle of the Southern Ocean. A lot of Earth's climate and heat transfer is controlled by the currents that are actually going around the Antarctic continent. And we'll zoom in and think about those more as we go. So that was, very quickly an introduction to the basics of where Antarctica is. Now I'm going to show you a little bit about what my students and I do, and how we complete our research. First off, I am a marine geologist. I work on the vessel that's shown in the back here. That is the Nathaniel Palmer. It is the U.S. National Science Foundation's research icebreaker. It's a 308-foot long vessel, and it is a class 2 icebreaker so that we can break through about a meter of first-year sea ice while maintaining forward motion. The vessel in the front right here is actually smaller. This is just sort of a funny picture, but this is the Lawrence Gould. It is ice strengthened, but not an icebreaker. I am a geologist. I'm studying the Antarctic ice sheet, but very much from the perspective of being a geologist. So we take a variety of types of samples from sediment cores. This one here, this is my students. We're collecting a Caston core. So this is about 700-pound weight, a 10-foot barrel. Sorry for switching between Celsius or metric and English units, but when we get into coring, it's all based on oil industry technology, so it's in feet. And so this is a gravity core. It's just pushed in by that weight. We also take much longer cores. This is me collecting a piston core. This is a jumbo piston core. The maximum length on this is 24 meters. It has a 2,000-pound head here, and then the piston is pulled up from this core catcher so that in soft sediments, we're able to get pretty long records without drilling. Our cores are part of the U.S. Antarctic program. Therefore, we're not able to bring them back to Houston. They are stored in national repositories. It used to be in Florida, and now it is in Oregon. It's like walking into a Costco-sized building with racks of sediment cores stored at about 2 degrees Celsius. We do also collect seismic data. I know this is low technology compared to the oil industry, but we are not able to tow long streamers because we tow in floating sea ice. And therefore, the only very short streamers are able to be used for our seismic collection. And what you can see here then is just a 210 cubic foot air gun. Multi-beam swath bathymetry is another tool that we use for collecting data here. This is, completed across the Gulf of Mexico and much of the North Atlantic. Almost everything has been multi-beamed at this point. But in the Antarctic, the seafloor is still relatively unknown, and therefore we do spend a fair amount of time simply mapping, doing the swath bathymetry style surveys to see what the seafloor geometry is like. And swath bathymetry in the Antarctic is pretty exciting because that continental shelf was glaciated during the last glacial maximum. Ice flowed across the continental shelf, carving across it. And the Antarctic ice sheet today is actually significantly retreated from its maximum position. And so this image here is swath bathymetry with the orange or warm colors showing shallow water, and then the blue or cool colors showing deep water. And obviously that is not river incision, it's not faulting, it's carved by ice flow across there. And so we're able to map where ice used to be from the continental shelf. The icebreaker, which is shown in the back of that photo, is a shared resource. It is a privilege to get to work there. But because it is a federal resource, around $1 billion, none of us work alone when we are out there, but rather we always have to collaborate and share the resource. In this case, we are working with some sea ice ecologists collecting diatoms from the sea ice. Because the air is quite cold most of the time when we're in sea ice, after the ship finishes breaking ice, if we wait around an hour, the sea ice will refreeze around us, and then we're able to get off the ship, walk on the floating sea ice. So in this case, we're in around 600 meters of water with about 1 meter of frozen ice across the top as a crust. And we can get out and walk around and collect these cores to get the diatoms that are living in the base of the ice. Of course, we work with biologists as well. That's a holothurian or a sea pig. There's a lot of soft-bodied organisms in the Antarctic due to lack of predators. And that was retrieved in a benthic trawl. And then with oceanographers, this is a CTD or a conductivity temperature depth recorder. You can see the rosette of bottles around it for taking water samples and water chemistry. I do also work with helicopters. The ship some years takes helicopters on board. It's an added expense, and so we don't always have them. But we do take helicopters not to go study the ice itself, but to go up to the nunataks or the places where there's small bits of rock that poke through the ice. And then we can set GPS stations there. Again, I'm not measuring ice flow as a geologist, but in the rocks, we're able to set GPS stations and then measure isostatic adjustment or rebound during ice melt. Because the helicopters are expensive, sometimes we also work in small boats. And so you can see, there we go, ashore in Zodiacs. We have to wear these float suits to go ashore on the beach. Of course, the problem then is that we have to walk up in order to do any work. Our target is not the beach, which is why it's nice to start with a helicopter. But we do work with what we have. Some years, including our most recent project, we do sub-ice coring. And this is in collaboration with the British Antarctic Survey as part of the Thwaites Glacier project. In this case, I want to clarify that I've said sub-ice coring. It is through the floating ice shelf. And so we just melt a hole with hot water through the ice and then drop a regular short piston core through it. So this is not drilling, it's just short cores, but reaching farther under the ice to do it. Working with oceanographers, we do also work with AUVs. This is the AUV Ran, named after the Norse goddess of the ocean, Ran, although she was lost at sea this year. So this AUV is still out there in the ocean somewhere, unfortunately. And finally, we work with totally autonomous assistance at some times. You can see the seal here in the photo with a satellite transponder and temperature recorder. Because of sea ice, we're usually only there for maybe January to April at best. That's the austral summer to early autumn. And that leaves 8 months of the year where there's no scientists there able to work, able to get any oceanographic measurements. As a geologist, we're not that interested in, being there in the winter versus the summer. It doesn't particularly matter. But to get a full picture of the oceanography and how ocean temperatures change by year, we need those winter measurements. And so as part of our project in both 19, 20, and 22, we worked with oceanographers that can anesthetize seals, glue a transponder to their head, and this transponder will continue to work until the seal molts, which will be about 11 months later. And wherever the seal goes, the temperature is recorded, and then when they surface, that information is sent to a satellite. That's actually how we know most of the winter details. Back at the University of Houston in my laboratory, of course, the work doesn't just end in the field and we come home and we're done. Most of the labor is done on campus. This is a picture from my lab of a Canberra gamma ray spectrometer. The lead shield right here is 4,000 pounds. That's what the steel plate at the bottom is for, is to spread that weight. My lab's over the dean's office, so I was instructed to be very careful to put that plate there. That 4,000 pounds of lead is not because we have anything particularly radioactive, but it is to keep the background dust and radioactivity away from our samples because we're measuring very low levels of decay. I measure gamma rays from lead-210. Lead-210 is part of the uranium decay series, but has a very short half-life of about 22 years. And therefore, when we measure it, we can only go back about 100 years, or about 5 half-lives. That's okay, because a lot of what I'm doing now is actually studying how the ice has changed since about 1900. In addition to lead-210, with the same samples, same measurements, we can also sometimes record cesium-137. Of course, cesium-137 is not natural, it's a bomb product. And so when it is found, it is from either nuclear testing or Fukushima or other nuclear accidents. In the Antarctic, it's very rarely found, and the only spike that we're able to find is 1963 following the nuclear test ban treaty. But being able to have 2 independent measurements and peg 1963 into the lead-210 time series gives 2 independent chronologies and a good check to make sure each is working. And I also do grain size and shape and texture. This is a very standard laser particle size analysis system. I use a stylus with 3 lasers, but it's basically the same as any Malvern or other LPSA system. For measuring grain size, this one goes from 2 microns to 2.5 millimeters. And it is attached to a microscope, and the same aliquot of the sediment runs through the line, through the microscope. Digital photos are taken of every individual particle. We run those through a small MATLAB code. You can see my student sitting here working. And each of those individual grains is then transferred to a binary image. And we do a Fourier analysis of the roughness coefficients. And that's useful for understanding if the particles have been transported purely by water or purely by ice or somewhere in between. And then lastly, this is an SEM image of a sand grain. And then we look at the individual textures, which again, show transport mechanism. Okay, so that's just a picture of us. Sometimes I show drone shots, but that's a helicopter shot of our vessel. So why do we do all this? You know, it's a lot of time, it's a lot of money, it's a lot of equipment. Why is this worth it? Okay. If Antarctic, okay, I'm gonna change that. How much and how fast is Antarctica contributing to global sea level? I told you earlier that if Antarctica were to melt entirely, global sea level would rise about 60 meters. But that is not being predicted or modeled or expected. This plot shows the year 2000 to 2100 on the x-axis. And then on the y-axis, we have contributions to global mean sea level in meters just from Antarctica. So not what's predicted globally, but what might happen from Antarctica. And if you're familiar with the IPCC reports, these are representative concentration pathways, where the lower numbers represent sort of conservative, less burning Paris Accord numbers, and the higher numbers represent more fossil fuels, more burning, more CO2 in the atmosphere. And so this is to estimate how much sea level will go up just from Antarctica. And you can see that the numbers range from about nothing, 0, which is the low estimate for the low CO2 contributions, to almost 1.5 meters. That is a huge range. And what is unknown there is not global temperature or CO2 levels, but unknown how Antarctica will behave. So this is a pretty famous paper by DeConto and Pollard from 2016, and it's followed up by the same authors in 2021. And I'll note that this is approximately the same diagram. We have the year 2000 to 2100 on the bottom axis, change in global mean sea level on the y-axis, but note that now it's going just from 5 centimeters to 30 centimeters at the top. And then the various, again, scenarios. This is the newer IPCC, so they're written in different ways. But again, it's the high temperature, high emissions, or low temperature, low emissions. And the range now is much smaller. So there's one unknown, and that's human behavior, and that's what's represented in all of these lines. But the other unknown is the ice behavior, because really all of these have massive air bars on them, where we don't know how the ice is going to behave to temperature change. And more data is required to improve predictive climate and ice sheet models. So I'm part of a project working at Thwaites Glacier. Here you have Antarctica again. This colored image shows the velocity of ice flow, with the browns representing slow flow and the purple, pink, red representing the rapid flow or ice streams. And so you can see that ice behaves a lot like water. There's drainage divides here in East Antarctica. And then as the flow gets focused and comes together, the velocity speeds up into a few of these major outlets. In West Antarctica, Thwaites Glacier and Pine Island Glacier sit next to each other here, flowing very rapidly. In addition to flowing rapidly, they are changing very rapidly. In this diagram, we're thinking about how much ice shelves, that floating part of the ice, has thinned or retreated in about 30 years. And we're not going to worry about the numbers exactly too much, but red represents ice loss and blue represents ice gain. And the size of the dot represents the percentage change. So it's pretty easy to see really quickly. There's a few small blue dots over here, but there's a lot of big red dots right here. And that's why we are focusing our work here at Thwaites Glacier, because it's flowing rapidly and it's changing rapidly. So I told you earlier that East Antarctica and West Antarctica were quite different. West Antarctica is a marine-based ice sheet. And so you can see the ice sheet here. Here's the ice shelf and the ocean out here. And what we mean by a marine-based ice shelf is that it is grounded below sea level. And that means ice is in contact with water. And of course, there has to be a temperature difference across there if we have warm ocean water reaching colder ice. Now, because this water is salty, we can actually have liquid water at minus 1.6 degrees, and much of the ocean is. But there is a warm current that comes in, and warm, I mean +1, maybe 0.5. Doesn't have to be very warm to be warmer than ice, and it will melt that. The other thing in this marine-based ice is that the continental shelf is sloped backwards. And that means that if ice is going to lose its footing right here, it's even harder to gain it here, and even harder to gain it here. It gets harder and harder for it to reground. And so marine-based ice is considered ice at risk of sudden change. So I am the PI of a project called THOR, which stands for Thwaites Offshore Research. I work with a huge team of people, and I have co-investigators from Rice, Florida, UK, Alabama, Columbia University, and University of Virginia. We are funded by National Science Foundation, as well as by the National Environmental Research Council in the UK. And as part of this THOR project, we are collecting a range of data. And again, here's this grounded ice, here's floating ice, here's our ship. We are collecting multi-beam, we are doing towed geophysics, we are taking sediment cores, both from the ship and from the floating ice. And then we are working with oceanographers to determine how this warm water is coming up and reaching the ice today. And then we are using the sediment cores to determine how that water temperature has changed in the last century or the last millennia. What I'm going to show you today is sedimentology results. And so with sedimentology, I can tell how the ice has moved back and forth, right? We can look at the sedimentology and tell if it was deposited by ice or deposited by ocean. But then we also, coming up, will work with micropaleontologists collecting forams when they can be found, and diatoms especially, for reconstructing paleo water temperatures. Okay, so what have we found? This is the last section for this talk. What have we found lately at Thwaites Glacier? This is a complicated diagram, but I think it's a really important one to understand what's happening as a modern day climate and as a geologist. This is published by one of my colleagues, Ali Graham, in 2022. This is in Nature Communications. These 5 black and white images are side scan sonar. So you can think of them as the equivalent of an aerial photo. They are sonar images of the seafloor, taken from that AUV I showed you earlier. In the colored images, these are multi-beam swath bathymetry data, and they are, let's say, equivalent to a LiDAR image. This is showing the bathymetry on the seafloor, where we have deep water in purple and shallower water in these green colors. In all of these images, the arrow is pointing in the direction of ice flow, which is broadly to the northeast. Excuse me, northwest. Those look like tire tracks. These look artificial. They look fake. They look like noise in the data, or they look like we have imaged a tire track on the seafloor. However, this is in about 1,500 meters of water, immediately offshore Thwaites Glacier. And what those are is small grounding lines. Each of those is a tiny little glacial moraine, just like you might see in Montana or the Alps or Alaska, a small little glacial moraine recording a pause or a place where the ice paused for a moment and then stepped back, continued to carry sediment, stepped back. And because about 160 of these ribs or rib moraines were found in a row here, we're able to do a little Fourier analysis and see that they're actually tidal. How do we know they're tidal? They have a 14-day or a 14 periodicity. There's nothing else in nature that's going to come up with a periodicity of 14. So how do these form? Here is a cartoon. Again, we've got ice sheet in the back, grounded ice. Here is the floating ice. And here is the ocean cavity under that floating ice. This is obviously not to scale. You can draw another kilometer of ice on top of this if you want. We're focused down in here at that little moraine. Because the ice is floating, every tidal cycle lifts it up a little bit. And then the tide goes out and the ice sits down. And the tide goes in and it lifts up. This actually happens for many kilometers under the modern day ice sheet. This is known from synthetic aperture radar data that you can see the ice go up and down every day with the tidal cycle. And out here in the margin, that affects how the sediment is being deposited. And so during one phase, the ice will be pinned and the little rib moraine is deposited, the tide comes in and the ice steps back. And then during the next low tide, the next rib is formed. I think the best analogy is to imagine walking in galoshes in a mud flat, and every squish, you're making a ridge with your footprint into the mud. But now just imagine walking backwards, and that's how these ribs are being deposited. So measuring those distances and knowing that they're tidal shows us that ice was retreating at approximately 3 times faster than has been seen today. Faster than any people or any satellite have seen retreat. Thwaites has retreated at 3 times faster in the past. Now, we don't have a date on these. Maybe they were 200 years ago, maybe they're 1,000 years ago. So this is not an exact point in history, but rather saying that the ice can retreat more quickly than we have yet seen. And that's my first conclusion, is to say that ice has the ability to retreat faster than we have seen. That's something that's important to know about glaciology. And it's also the reminder that paleo teaches us about ice behavior that is not otherwise seen. Geologists and paleontologists have a critical role to play in understanding ice sheet behavior, because observational data is, by its very nature, limited only to what has been seen now. So as a sedimentologist, we work on those cores, of course. And this is a cartoon showing just a basic facies model. This was drawn by one of my students, Rachel Clark, and we'll show you her publication in a moment. So right here under the ice, whether that's under the primary grounding line or under a pinning point, we get these very coarse, poorly sorted, classic glacial sediments. In zone 3, out in the open ocean, because there's sunlight in the ocean, there's diatom or phytoplankton, and we have rapid deposition of biogenic sediments. And zone 2, under the ice shelf, is this relatively low sedimentation rate zone where we don't really get the glacial sediments and we don't really get the ocean sediments. It's somewhere in the middle. And so working at Thwaites Glacier, of course, as a geologist, we're reconstructing facies over time. And we started the bottom with that subglacial till. This is the core photo on the left. This is the cartoon of it on the right, showing that we step from the grounded ice into gradually less and less proximal facies into this transitional sub-ice facies, and then eventually into the seasonally open marine. And remember, this is still covered by sea ice in the winters now, so that's why it's seasonally open. And then just to show you all the types of data that we use in the sedimentology side, here is a digital core photograph. Has this gray stripe through the middle. That is X-ray. We then have our cores CAT scanned. Excuse me. Sometimes I work with Halliburton for CT scanning. This particular one was actually done at the Oregon State Vet School. Hospitals don't usually let you put sediment cores in, but vet schools will. And so we have the CT scans, density logs, shear strength, magnetic susceptibility, pebble counts, which is a measure of ice rafted debris, grain size, plotted a few different ways here with skewness. And then here's water content. And then out here is that age model with lead-210 activity. So we do that a bunch of cores, a bunch of places, etc. And this is what we have reconstructed at Thwaites Glacier. And this was published earlier this year in PNAS. At Thwaites Glacier, which is down here at the bottom, this is open ocean at the top. Before the 1940s, we had grounded ice at the Thwaites Glacier tongue and at the Eastern Ice Shelf tongue. And that grounded ice was pinned on the seafloor highs and holding back this larger area of ice. And again, we know that from combining the sedimentology with our age models. From the 1940s to the 1970s, that ice began to unpin, and we started to record actually that warm water reaching up to the ice. And then in the modern day, this is the configuration we have today with our cores right around the ice. We still have this warm water. This is significant in here because the 1940s is a time of a large El Nino cycle. I know everybody hears about El Nino, and the El Nino is just ending and we're going into a La Nina. The El Ninos have, through teleconnections, ties to polar weather as well. And so the El Nino pushes the currents farther south. And what we found in this paper and why it made it to PNAS is that the Thwaites Glacier retreated at the same time as Pine Island Glacier. And if two glaciers adjacent to each other are retreating at the same time, they're almost certainly forced by external drivers. So this is the first time now we can say that Thwaites has responded to global climate. So for my last Antarctic figure, this is a new paper. This is by Smith et al. In 2020. And again, here's our favorite Amundsen Sea area with Thwaites and Pine Island glaciers. And as always, we use the red or hot colors to indicate warming or ice loss. And we use the blue colors to indicate cooler or less ice loss. And right here in Thwaites Glacier area, you can see that's the concentration of red. This is the fastest changing area. And we're looking at it here, just that period from 2003 till 2019. We have continued to lose ice each year with more and more ice coming across the grounding line each year. So what that means is that we found in our paleo work that ice can move faster than we've ever observed, that Thwaites and Pine Island were kicked by that El Nino. But as we continue to watch it, we can say that once it was initiated, the retreat continued well past the time the forcing mechanism was removed. So the ice retreat, in this telling anyway, is unstoppable, that it will continue to retreat even if the driver is removed. So that's really, I think, where I'll leave it. There's a few other slides, but that's the meat of it. And I think I'll stop here with this pretty drone shot of us at Pine Island Glacier and take any questions from you.
Thank you very much, Julia. That was wonderful. I think there are some questions in the chat.
Okay.
Yep.
Do you want me to?
Go ahead if you want to answer them.
Okay. Okay.
There's one by O. I'm not sure that I mean, oh, I'm not sure that I know what that means, but something. Then Christopher Motter is saying, I'm missing something and maybe everything. What is the time frame between the tire tracks, mini moraine?
A day.
Yeah, that was before you talked about tides.
Okay. Yeah. So that was a day. And then here is somebody at 1229. What is the adjective? I think you're going to have to answer or ask questions by voice or retype if you want, because the question here says, what is the actual data point measurement and how is it substantiated? I don't know which data point. So I'll just invite new questions if you want.
Yeah, you can raise your hand and Wendy will let you speak. So.
I see somebody with their owner has raised their hand.
Yes. Hi. Excellent presentation. Thank you so much. I had a question on your table. I can't remember which one it was now, but it was like halfway through, where you were showing the plot of the changes over time. And I was just actually asking what the actual data point measurement was.
Like this?
No, it was an actual data plot. I think you just went past it.
Here?
Yes.
Okay. These are models.
Right. But what are the actual data points?
Oh,
what is a measurement?
Okay. So these are models of the future, and ice sheet modeling is a complicated field unto itself. So these are physics-based models of ice behavior. And the particular ones that I'm showing you, and the reasons I like these, is that they are tuned by looking at the past. And so again, I am not a modeler. I don't work on the future. I work on the past. But these particular ice sheet models take into account sliding, basal sliding, ice deformation, crevassing, melt and air temperature and ocean temperature. So there's a whole bunch of sort of physics of ice flow in there.
So there are a
And
lot of
this-
assumptions.
Yes, but absolutely. But these particular models, and the reason these are among the better known models, is that they are calibrated by geology. And so there are certain ice sheet models, and again, this is a whole field. It's like, there's hundreds of ice sheet modelers out there. Some are just based on physics. These particular ones are physics-based models that are then tuned to, say, the Pliocene sea level, or the Miocene sea level, or the mid-Pleistocene glacial cycles. And so these particular models have been proven to match past sea level records. And therefore, there's more confidence in these about making future predictions.
Thank you very much.
Sure. And then I'd say, yeah, I agree. There's some assumptions. And that's the whole reason that I'm saying we need to know more about how ice behaves. And, why NSF funds this work is that while their models are getting better and better, and the unknowns are getting smaller and smaller, fundamentally, there are still unknowns about how ice will behave and why we need to look at it.
Thank you.
I have a question about the tire tracks.
Yeah.
Do you think they could be observable in areas of Pleistocene glaciation?
Yes. So these are analogous to Rogan moraines, sort of. So
Yeah.
moraines that are well known in places like Sweden and Norway.
Yeah.
They're not identical because they are marine based, and any moraine that is forming on land by definition won't have tidal influence on it.
No, right.
But yes, absolutely. These little rib moraines are quite common across Scandinavia.
I've never seen anything like this in a land in an old moraine, but it seems to me that if you have gaps in the VARV record, you could use these to fill those gaps, possibly.
Absolutely. Go ahead.
I was saying if you could find them.
Yeah, the problem with looking at little moraines like this on land is that, you get trees and, animals, so there's all sorts of difficulties to see. And sometimes marine is actually easier. But yes, absolutely. It would be great to find records like this tied to varves or other things on land. Yeah.
Okay, there's another question in the chat here.
Okay.
If I'm understanding you correctly, does the speed and/or movement of the ice, indicated by the paleo ribs, being the fastest movement never seen today, correlate to the ice retreating and sloughing? I think that's what it said.
Yeah, so again, I'm going to do my best with your question and just jump in again if I miss the question. So the paleo ribs, the fastest movement, you're right, hasn't yet been observed at this glacier. Yes, the ice was retreating at that time. In the Antarctic, the ice has been retreating for about 20,000 years. just like in the Northern Hemisphere. So you know that the Holocene, about 10,000 years, and the last glacial maximum ended about 18,000 years ago in the Northern Hemisphere. And ice has been retreating across North America and Europe since then. The same is absolutely true of the Antarctic. During the last glacial maximum, ice reached the shelf break in the Antarctic and has been retreating at different rates ever since then. But most of that retreat happened from about 20,000 years ago to about 4,000 or 6,000 years ago. And so I didn't show a sea level curve in this talk, but if you look at a sea level curve of the latest Pleistocene and Holocene, sea level rose very quickly from 20,000 years ago to about 5-ish thousand years ago. And we've been in a sea level still stand for about 5,000 years and now starting to pick up again. So this time is from some past time of retreat.
So this highest sea level in 5,000 years ago, that corresponds to what we call the hypsithermal in Northern Europe.
Yeah, it's not the highest sea level. It's just the end of the rapid rise. So it's still coming up over the last 5,000 years. It's just coming up slowly rather than rapidly. But yes, there are hypsithermals throughout this time.
Yeah. Now, another question I have, if nobody else is asking questions, is clearly there's a well-established long-term correlation between what's going on in the Arctic and in the Antarctic. But my question is, does that hold up over very short periods of time, or are there distinct differences between the two hemispheres?
There's definitely distinct differences as you get to the short time scales like I'm working. So yes, on the largest scale, sort of the Pleistocene glacial interglacials, yes, the two hemispheres are working in sync. But on the decadal or centennial scale, they're quite different. And that's because with the Arctic Ocean, it is largely controlled by air temperature. And in the Antarctic, at least in the West Antarctic, this marine ice is controlled by ocean behavior because the ice is sitting in water for the most part. And what that means is they have independent controls. But more than that, East and West Antarctica behave differently. Just like does the Mississippi River get the same signal as the Rio Grande? No, not at all. In Antarctica is about the size of US and Mexico combined. And so there's really no reason to think that individual drainage systems will follow the same advance and retreat pattern. But
go ahead.
I was just going to say that so there are certainly differences in both Arctic and Antarctic systems. What we can say, though, that across all of West Antarctica and the Antarctic Peninsula is that they are retreating for the first time since at least the last glacial maximum. We have all of West Antarctica in a retreat mode at the same time.
We do have a couple questions.
Yeah, we do have a couple here.
Why did sediment not fill in the tire tracks?
Excellent question. That's a great question. So the sediment that would have filled them in, if you mean ocean sediment, that would be coming in today, it just hasn't had a chance yet. So the sedimentation rate in the sort of biogenic open oceans, pelagic sedimentation there is a couple millimeters per year. And these tire tracks are on the order of maybe a meter, and they just haven't had a chance to fill in yet. I say that's a great question though, because we don't have an exact age on these tracks yet, because there's no core here. But trying to think about how much might be filled in versus the regional sedimentation rate, it's just a really fun question to think about. The answer is we haven't had time, but it's still something really interesting to think about.
All right, looks like we'll take one more question here. Any idea what might have caused that retreat 4,000 to 20,000 years ago?
Sure, that's from the global insulation. So in general, Earth's glacial and interglacial cycles are controlled by Milankovitch cyclicity. That is the shape of Earth's orbit around the sun. And so our orbit around the sun is not a perfect circle, but rather it's an ellipse. And that ellipse sort of gets bigger and smaller, more circular and less circular over time. There's also the tilt of our axis of spin changes. And collectively, those changes in how Earth's orbiting are called the Milankovitch cycles. And that changes how and where Earth's receiving energy from the sun. And that controls the large scale glacial interglacial cycles on Earth. Insulation.
I had, at the risk of running a bit over time, I had one follow-up question about the retreat from the ice shelf and from the continental edge. And my question is the fact that the ice reached the edge of the continent, where the slope begins, a self-limiting factor, and as it retreats back, is there some other self-limiting factor that will stop the retreat?
Awesome question. And yes, absolutely. I'll go to this diagram just for example. So this is the continental shelf here. During the last glacial maximum, ice was grounded out about to that shelf break. But yes, you're absolutely right. That is self-limiting. Ice cannot then prograde and ground down the slope in deep water. That's just not possible. And so the maximum sea level fall, and if you look at like the hack curve of global sea level cycles over time, there's always sort of the same limit about how low sea level gets. And that is absolutely controlled by that shelf break.
Wow.
You asked, is there another self-limiting change on the other end? Where it can only go back so far? No, unfortunately. Like that would be great, but no.
Yeah. Whereas I don't know if it's important to factor, but in the Arctic there is. You can have either complete ice cover or no ice cover.
Yeah, exactly. Because the Arctic sea ice is just sea ice, right? It's really not part of the sea level cycle. I mean, it's important for polar bears, and it's important for the Navy and for global shipping. But the Arctic sea ice is not part of what controls global sea level.
No, but it does control insulation in the northern hemisphere.
Albedo, yeah.
Albedo, yeah. So there are two sort of end states of total albedo for the northern hemisphere, which might affect the magnitude of climatic.
Yes, absolutely. In many steps, it's not a simple sea level tie like it is here.
No. It's very interesting. I haven't thought of these things before.
Julia, on that question about the 4,000 to 20,000, the person followed up saying, so not anthropogenic?
No, anthropogenic change really begins around 1850, then with clear signals since 1950. Anthropogenic change is much shorter time scale since the Industrial Revolution. But that's also why we do the work that we do. A lot of our papers now are called the pre-satellite record. So I just said change began around 1850 to 1950, depending on exactly what we look at. And satellites begin to tell us what's happening around 1970 or 1980. And so if we want to know what is the state before anthropogenic ice sheet behavior, we can't do it just from human observation. There was no one there and the satellites weren't looking. We have to use the geologic record with this lead-210 short-term radiogenic dating to go back just before 1950, back to 1900 or so, to get us into seeing what was the natural state before these changes began. And let me just add, in case the person who asked that question is a specialist in Holocene climate or anthropogenic climate, and you're saying, well, what about farming and the idea that anthropogenic change began 10,000 years ago? Yes, you're right. There is small scale change that begins 10,000 years ago due to the onset of farming. Different scale.
Yeah, I help archaeologists in Southern Europe, Sicily, and so forth.
Yeah.
And it's amazing once farming starts how rapid deforestation is in these areas in particular.
Mm-hmm.
So, okay.
Well, Julia, thank you so much. We've had so many positive comments in the chat. I don't know if you've had a chance to see it, but very, very thankful for the informative presentation, and we really appreciate your time, and presentation was outstanding.
Yeah.
Thank you very much. I appreciate that.
And I think we're over time, so it's probably time to close it. So thank you very much, Julia.
Thank you.
It's been wonderful.
Okay,
Yeah,
thank you all.
Take care.
Bye.
Thank you.